It's my pleasure to introduce Malcolm. Harold, who's in it, currently in Europe, and he's going to talk to us about approaches to groupoids and C-star algebras. Thank you.
Thank you, Tristan. Thanks for the invitation. It's a real pleasure being here. Thanks, Ben, for the great pre-seminar. It means I can get through a few things a lot faster, which is nice and efficient. And hopefully there are still some interesting things beyond what you've already said that I'll share with you. So thanks everyone for sparing the time and being here. Um, yeah, so the plan is to sort of start by saying what are C-star algebras and how might we try to understand them? So that's number one. Number two, and so far we're just refreshing what Ben's already told us. How can we understand them from groupoid C-star algebras? And then number three is how can we think of C-star algebras from graphs via groupoids once we have the tool to get a C-star algebra from a groupoid. And then four will be what happens when we have this higher dimensional version of a directed graph called a higher rank graph, particularly in the finitely aligned case, some finiteness condition that makes them easier to handle. And then right at the end is this non part because the non-finitely aligned graphs are really badly behaved, and that's what I spend most of my time grappling with. Uh, so that's the rough plan. So as we've seen, there's ways of constructing C-star algebras from other objects, like from some topological space or a group classically, and in more recent times from groupoids as well. And uh, starting with topological space by Gelfand duality, we know that if we have some commutative C-star algebra, then A is homeomorphic to the continuous functions vanishing, isomorphic to the continuous functions vanishing at infinity on some locally compact Hausdorff space, X being locally compact Hausdorff. And this way of realizing the C-star algebra A is powerful because, among many things, we could say that the ideals of A correspond with open subsets in the underlying space. So this is the kind of result I want to trace throughout the talk. If I then try and build a C-star algebra from a groupoid, can I get some other description of its ideals via the groupoid? And if we do it via graphs instead, can I see the ideals via the graph? Uh, so let me just leave a little bit of space, and I'm going to eventually have some kind of a theorem here about groupoids, and then eventually I'm going to have a theorem here about graphs as well. Um, and as we saw from Ben's talk, uh, the matrix groupoid, if I have the natural numbers up to n, and I look at all pairs of these natural numbers, this forms a groupoid that allows me to recover the n by n matrices over complex numbers. Slightly more generally, we could look at any equivalence relation um, on a set. So the groupoid of an equivalence relation R on a set X is the pairs xy, where x is related to y, under the operations I know x is related to y, uh, then I'll compose it with something only if the left element of the other tuple is also y. And I just witness transitivity and I say, well, then I also know x is related to z. So I have some well-defined composition of these related pairs. And inversion witnesses the symmetry in the equivalence relation. And because equivalence relations are reflexive, I'll get the unit space GR naught is all of the pairs XX or X in X, which identifies with the set on which I have an equivalence relation again, X. Um, and so we've seen already path groupoid of a directed graph has a similar flavor, but there's just a little bit of extra data in there as well that keeps track of how many times you have to perform these shift operations and delete parts of infinite paths. Um, so for the most part today, the kind of groupoid we're going to be interested in is of this flavor. So maybe try and keep that picture in mind. And still sort of revising what we've seen before, if I've been given a groupoid G, a really nice groupoid, and just like Ben did, I'm going to say, I'm not going to say what nice means. I'm going to hide really a lot of adjectives in there, which is going to allow me to put a lot of stuff on the board. But feel free to quiz me and say, well, how on earth should that be true? Um, Examples of adjectives included in the word nice today will be that the groupoid is étal, and in fact, often it's going to be ample today, it's going to be Hausdorff. The groupoid's amenable as well, which will tell us that the two constructions of C-star algebras Ben showed us actually coincide. There's just one completion of the star algebra we build from a groupoid, so there's really a lot that I'm assuming here. But really key thing, one nice thing that I do want to highlight is that the unit space is locally compact and Hausdorff. Because this local compactness of the unit space is the part that starts to really cause trouble once we get to this world of non-finitely aligned higher rank graphs. So that's the one thing that seems innocuous that I am going to emphasize is that we really want our underlying space to be locally compact. The unit space. Another reason to see why that might be important is that we want our groupoid to, inside of it, be encoding what Gelfand duality gives us. That if we have some nice commutative subalgebra, then its spectrum should be able to recover the continuous functions just supported on the unit space. So we're looking for a sort of non-commutative analog of Gelfand duality. So when you're in such a nice setting, as Ben pointed out, we can construct a star algebra by collecting all of the continuous, compactly supported functions from the groupoid to complex numbers. And if we endow this with convolution, and a star operation defined as such, then this is a star algebra with star algebra, and having assumed the groupoid is really nice, there's really just one completion I'm interested in. So it's a star algebra, and the completion is its groupoid C star algebra. And to try to make these operations more familiar, one thing to try to puzzle with in your head is if I take G to be the matrix groupoid Ben showed us, where I've got all pairs of natural numbers up to n, the size of my matrices, then this convolution is just performing matrix multiplication. Because I say, look at some index, some row, column, entry in my matrix, and with respect to this index, I take a dot product of all of the row and the column that have that right index, and look at what the values were in the two matrices that I'm multiplying together. So convolution product is really like generalizing matrix multiplication. Involution 2, the gamma inverse I've got here, it's an equivalence relation groupoid, so I'm just swapping the order of the terms. So I'm swapping my rows and my columns, and then I'm taking complex conjugate. So that operation is my conjugate transpose of a matrix. So this might be one reason why we say that groupoids can coordinatize a C-star algebra in the same way that a matrix algebra is coordinatized by row and column indices. Okay. And again, keeping track of what this underlying space is doing inside of the C-star algebra of the groupoid, there's a nice commutative subalgebra of continuous functions vanishing at infinity supported on the unit space. And do just shout out when you have comments or questions, or if I say anything silly at some point, just tell me before I get too carried away. Okay, so that takes us to part two. So again, I'm just sort of reviewing what Ben's already told us. So hopefully it's useful to sort of see it again. I need to see things many times before it actually enters my head personally. So then we want to talk about graph C-star algebras, and because we have this machinery of getting from a groupoid to a C-star algebra, one way to do that is to say, can I build a groupoid from a graph? And then I have my C-star algebra, if the groupoid's nice enough. So, given a directed graph E, given a directed graph E, this is my edge set. As Ben already showed us, the path space. And with the graph itself, I'm also going to ask for it to be nice, and Ben did even better than me giving details of what nice can mean. It's things like the condition that I'm gonna want at every vertex that there's kind of enough things going into it and out of it, but not too many as well. So we have lots of conditions that we impose, but if it's nice enough, then we can define a path space. I'm going to write xe for the path space, or in Ben's notation, E infinity, which is standard notation. But I'm gonna be writing down a lot of path spaces today. So I just want a systematic way of saying a path space of this thing and then a path space of the other thing, etc., etc. So what does this look like? It's a it's the set of infinite parts of edges where indeed I only put two edges next to each other if there really is a path. The range of one of them is the source of the other one. And on this path space, I can define a shift map, sigma, by I need sigma of infinite path. Just deletes the first edge that you see in the path. Move one step forward. And the path groupoid GE is the triples x m minus ny, where if I take the first m edges off of x, I get the same thing as if I take the first n edges off of y. With operations x, k, y, y, l, z is x, a plus lz, and x, k, y inverse is y minus k, x. And there needs to be some topology, but also that's just not going to be relevant to the very final point that I'm hoping to get to today. So let's just say that in a similar way that you might well, no, I'm just going to give none of the details actually. Just take my word for it, and if it becomes like really relevant and you really want to know, ask. But you can put a nice locally compact Hausdorff topology on the path space, and extend that to the whole groupoid in such a way that it does satisfy nice. And because it satisfies nice, we can build a C-star algebra, and we have a graph C-star algebra. And one of the important papers showing us the graph approach to C-star algebras via groupoids. One of the seminal papers is by Kumjin, Pass-Grayman, Rayburn, and Renaud, 1997, where they actually define the graph C-star algebra in the paper to be the C-star algebra associated to the groupoid. And then they show later in the paper that if you do this, then you can also describe the C-star algebra via natural generators and relations. Is the graph C-star algebra. And as a subalgebra, commutative subalgebra, we have the continuous functions on the path space vanishing at infinity. So we have some way of building C-star algebras from groupoids, and we have some way of building C-star algebras from graphs via groupoids. And why would you want to do this? Because among many things, it gives you a way of describing the ideals in the C-star algebra. So Renaud's groupoid approach to C-star algebra, which is what we're seeing today, going back to his monograph in 1980, he showed that if your groupoid is as nice as I've told you it is, then the ideals, so for nice uh, groupoid G, the ideals of the groupoid C-star algebra correspond not just to open sets, but open invariant sets in X. I haven't said yet what invariant means. So Ben showed us this nice picture of a groupoid, which looked roughly like that. And you have arrows. And the arrows really are the elements of the groupoid. And the space that the arrows are going from and to is your unit space. Open invariant subsets of the unit space. So invariant means that a set of arrows is invariant if, a subset of the unit space is invariant if, when I look at any arrow starting in the subset, and I look at where that arrow goes, it doesn't leave the set that I've started in. Okay. So invariant somehow means that it's closed with respect to the dynamics of the arrows that make up the groupoid. And Renault showed us that the groupoid C-star algebra, its ideals are in correspondence with the open invariant sets of the unit space. Then taking that further, Jim Pask, Rayburn, and Renault used Renault's approach to see that the C-star algebra of the groupoid, its ideals are in correspondence with the open invariant sets of the unit space. But if the unit space is a path space, maybe I can see that these are even simpler. Maybe it just depends on the graph itself and not the groupoid. So indeed, they showed for nice graphs the ideals of the C-star algebra of the graph. I haven't written it, but just for completeness, the C-star of E is the graph C-star algebra are in correspondence with saturated hereditary subsets of the vertices V of the graph E. Saturated, got a couple of pictures that should help to picture these things. And what does a saturated set of vertices look like? It means that if I have some vertex V in my graph, and I have a number of edges going into it, if I know that all of the vertices at the source of those edges are already in my set, then this vertex that they converge on also must be in my set. So that's what saturated means. And hereditary means that if I've got a vertex V in my graph and an edge going this way to some other vertex in the graph, hereditary means if I contain this vertex, then I have to contain the vertex that it came from via some edge. It's not super important for the rest of the talk, but the point really is that this graph approach to C-star algebras has simplified quite a hard question, what are ideals in my C-star algebra, into a really combinatorial problem I just have to kind of look at the graph and see where the paths take me from one vertex to the next. So that hopefully motivates us to keep talking today about graph C-star algebras, or what wider classes of C-star algebras we can get from graphs, because they provide quite a lot of insight into the C-star algebra from a much more combinatorial point of view. Any questions at this point? Comments? All right, so one criticism of the graph approach to C-star algebras might just be that your C-star algebra that you really love isn't in the class of graph C-star algebras. Maybe it's just too restrictive. There are bigger, badder C-star algebras out there. So what you might try and do is generalize the notion of a directed graph, make it a bit weirder, in the hopes that you can still build a nice groupoid so that you have a C-star algebra and a sort of just a bit more powerful theorem, a wider theorem in order to understand those C-star algebras. So that's what takes us to part 4 today, is what these higher rank graphs are, so that we can get a few more C-star algebras into this nice theory. So where I want to be. Yeah. So going back to work in 2000 by Kunjan and Pask, they define the notion of a k-graph where k is a positive integer. It's a small category, and we haven't exactly defined categories today. You don't need to know category theory. And as Ben said, some people say that a groupoid is a category where every arrow is invertible. So maybe I'll say that a category is a groupoid where not every arrow is necessarily invertible. And that should give you a rough picture. So a small category, really what I mean is I have a partial binary operation that's associative enough, and I have maps giving me left and right identities for every element in my category. And I'm going to call it lambda with a degree map D from lambda to the k tuples of natural numbers, including 0. I won't put the 0. Natural numbers have a 0 for today. Or always if you're a logician. Such that I have really nice factorization of elements in the category in terms of the degree map. So what I mean by that is if I can take some element in my category, compute, and see that its degree is m plus n for some k tuples m and n, then there's a unique element. There are unique elements mu and nu, so that the degree of mu is m, the degree of nu is n, and this path lambda that I'm looking at is the composition mu nu. We call this the unique factorization property, which is very useful assumption to have on your category. The whole category, actually. So the whole, actually this next example will clarify what the degree map is trying to do. But if it doesn't, then let's continue talking about that. So the first example of k-graphs would be what do the one graphs look like if I just take my positive integer k to be 1? Hopefully I'll get back to a one-dimensional setting, which is a directed graph. And I do. The directed graphs correspond with the one graphs. How so? If E is my directed graph, then E star, the collection of finite paths in E. This itself, if I take to be lambda, and I define a partial binary operation on lambda on finite paths by saying I can compose this finite path with that finite path if they start and end in the right place. I'm concatenating finite paths. Together with the function d, which to each finite path says how long that finite path is. If there are n edges, then the d of the path is n, forms a one graph. And then let's step up the dimension a little and see how the degree map looks a bit weirder when we're in higher dimensions. Okay, so if I take k greater than 1, positive integer, and I take n to be, I more or less I want a k tuple of natural numbers, but I'm wanting to build a graph that kind of could be infinite in one direction, but there are dimensions now to worry about. So for each dimension, I'm allowing it to go out to infinity. So you take some tuple of natural numbers or maybe infinity in some dimensions. And to each k and n as such, we can define omega k n to be the pairs that witness when one of these k tuples of natural numbers is bigger than the other. So I'm just kind of looking at a grid in k dimensions of k tuples of natural numbers. So I look at, I'm going to use an L and an M. Yeah, L, M, and K into K, such that L is less than M is less than this N that I start with, the furthest that I want to go out. And this omega Kn is going to be a K-graph if I use my equivalence relation groupoid-like composition, where I say, well, a partial order is a transitive relation. So if I see Lm, Mn, then I just ignore the M in the middle and I go straight from L to N. And the degree map here, degree of Lm is just the difference. How far do you have to go between L and M? So it's the difference map. M minus L, defined pointwise in these K tuples. And these are all going to be K-graphs. Omega Kn with that degree map is going to be a K-graph. So I've got lots of templates of K-dimensional segments of natural numbers, essentially. Now, what we usually do to picture this, if I took, I'm going to do this. No, I'm going to get rid of that for now. Let's just look at these examples. So if I am in 2 dimensions, k equals 2, and I take n to be wanting to go, maybe I'll take 2 steps right and 1 step up in my 2 dimensions. Then what does the omega to 2, 1 look like? I've got my tuples of natural numbers. Mhm. And 2, 1. And they're like the objects in my category, but then I'm looking at when is one less than the other. So I've got arrows indicating those elements of the category. And I'm just making some arrows solid to indicate that the degree here of this arrow, I look at the difference, and the difference is a 1 in the first coordinate. So we think of it, that's the solid degree, that's the solid dimension. And there's a dashed dimension as well, where the only difference happens in the second coordinate. And what you start to see, the new phenomenon, that's the whole reason we've introduced all of these technicalities in multiple dimensions, is that if I label some edges, lambda, mu, alpha, beta, then we now have relations in our category. Whereas a directed graph is some free structure, in this 2 graph here, I have that lambda alpha. If I compute this product, I'm going to get just the arrow from 0, 0 to 1, 1, because that's how we define the composition in this category. But that's going to happen also if I go mu beta. I'm going to go 0, 0 to 0, 1, and then 0, 1 to 1, 1, and forget the 0, 1. So now you have relations on the paths in the graph. So 0, 0, 1, 1, which is also mu beta. But you don't have any relations in directed graphs. So it starts to become a lot more awkward just to even make sense of how should I define my infinite path space now? Because if I write down a string of paths in lambda, now I have to be careful about if there were some relations happening as well. There's extra data. Okay, so a little bit of notation for k-graphs in order to try and build some path space, because it's still our goal to make a path space, make a path groupoid from one of these higher dimensional graphs, and then see it C-star algebra. I'll write mu is less than lambda if and only if mu equals lambda for some nu in lambda. This is a partial order where we think of mu as being an initial segment of lambda, lambda being an extension of mu. Because remember from the directed graphs example, these categories lambda are like finite paths in a directed graph, not just the atomic paths themselves. They're sort of all finite paths. So this is a partial order. And we write rule kappa in lambda. I'll write kappa lambda for the set of extensions, things of the form kappa nu, when it's well defined, so nu in lambda. And I'll write square brackets around kappa for the set of nu that are initial segments of kappa. Just establishing some notation that we're going to need to keep track of. And and I apologize. I know that there's at least one person in the audience for whom, if you put square brackets around a thing, then you're looking at all extensions of that finite path. So unfortunately, the convention is as opposite as it could be in this case, but this is what we do. And now we're going to start building up path spaces. But at this point, because it's hard to see what a path should even mean in a higher rank graph, there are multiple ways of building up a path space. And that's part of where my work has been while I was doing my PhD thesis, is just understanding that these different conventions we have for describing path spaces is the same. So one way, using our omega kn k-graphs that we looked at over here, is to say that the path space of lambda, and I write an m also in the subscript for morphism, is a set of degree preserving morphisms x taking some omega kn, some sort of template of a path that's n long in k dimensions. We map this template of a path into our lambda in a way that preserves the structure of paths. It has to be a morphism. And we do that for all n k tuples of natural numbers or infinity. That's one way of doing it. The other way of doing it is to say, instead of just trying to index every partial step along the way to this n long path that you just walked, which is kind of what this domain omega kn is trying to do, index every step along the way, you could just collect up the initial segments that were required to get there. By which I mean, you could instead take the collection of filters of lambda with respect to the partial order that we've defined above. What do I mean by filter? Where x a non-empty subset of lambda. So now I'm just taking a bunch of finite paths in lambda. Is a filter if anytime I have two paths, mu, in my subset X, then there is some common extension of them in the subset. Mu are initial segments of lambda. So that's just saying if you want to walk somewhere in a higher dimensional graph and you try to go right and up, then you're going to have to meet up later and make sure you get to the same point at some point, because otherwise you haven't really gone somewhere. You've got to some multiple places at the same time, which seems a bit odd. But you also need to make sure that you, in order to get to any path along the way, you take every step possible to get there. So anytime I see an initial segment, I have to include that initial segment as well. And so we've got these two notions of paths, spaces that we can do in higher rank graphs. And in either case, the notion of shift map has to be adjusted as well. Maybe I'll try swap the boards.
You put again, like, how do you get between one and the other? Like, how do you go from the Greek word assuming multiple into okay.
So the map is to take the image of the degree morphism. So if you give me a degree morphism, then x of omega kn is a filter of lambda. And then it's uses the unique factorization that we get from the degree map to say if I have some filter, there must be a unique way for me to take all of the possible initial segments that I needed to get there. And that helps you reconstruct some degree morphism from omega kn to lambda. Yeah. So I kind of, this is why I like the filter approaches because it, in quite a natural way, eliminates a whole other structure that I would have to worry about. Now I'm just looking at subsets of my graph, which feels already more combinatorial than looking at all possible morphisms into my graph from the wider category of categories. Okay. So it gets a bit fiddly and detailed, so I'm not going to say how to define the shift map for degree preserving morphisms, for the path space made up of degree preserving morphisms. But I will say how to do the shift map if you're just looking at filters. So shift map for filters, uh, instead of just, because there are so many dimensions happening now, instead of just defining something like I take off the first step in my path, that doesn't really make sense anymore because there's a first step this way and there's a first step that way. So I need to be a bit more careful about how much or in which direction I'm shifting. So we say uh, for for each possible direction I could move in, we define the M shift of some filter X filter. So this thing is a subset of lambda to be the set of final segments after I've moved by a degree m. So it's the set of nu such that mu nu is in X. And the reason that this makes sense to do is that there's a unique thing in X that actually has degree n, which uses the unique factorization property too. So there's only one part of my filter which is in the direction m and goes that far, and I just take all of that off. So the shift map in the filter case for the path space of a high rank graph, it at least kind of looks like the shift map in the directed graph setting. You're just saying there's only so much I could take off in each direction, and I just do that. And then the path groupoid, is defined almost verbatim. Yeah, the path groupoid is defined verbatim. So path groupoid G lambda, where you've used filters, is defined the same. Now, the issue is that because of how many dimensions there are happening, this construction only works if we apply some finiteness condition. So uh, it's 10 to, isn't it? Yeah, okay. So we define lambda is finitely aligned if for all two paths I look at in my category, there's some finite subset that generates all possible common extensions of mu and nu. Formally, common extensions of mu and nu are all in one of finitely many extensions of some finitely many paths in the graph. So this finite alignment condition gives you a lot of control, and provided the graph is finitely aligned, the path space is locally compact. And the groupoid is nice. And that means that we can build a C-star algebra, and there's quite an extensive theory about how the C-star algebras of these finitely aligned higher rank graphs can be described from the dynamics of the higher rank graph itself, that it extends the theorems we saw in the beginning about graph C-star algebras. The problem is that there are graphs out there that are not finitely aligned. And I'm just going to try to quickly point at an example of a non-finitely aligned graph and how the notion of a path really falls apart. And in particular, the path space stops being locally compact to get to the kinds of questions I'm struggling with now in my research. So if we have similar to what we had before, we have a sort of skeleton of a higher rank graph, but we ask for there to be infinitely many edges on the top and the right-hand side here, countably many, infinitely countably many. And we impose the relations that lambda alpha n is equal to mu beta n for all n, then this thing is no longer finitely aligned, because if I take mu and nu to be mu and lambda, the common extensions are exactly these paths of the form lambda alpha n mu beta n, but there's no way to boil them down to extensions of some finitely many. They're all kind of disjoint from each other. So it's not finitely aligned, and we struggle to make a graph groupoid nice enough in such a situation in order to study its C-star algebra. The prevailing method for handling such graphs that Spielberg developed in a series of papers in 2012, 2014, and 2020 is to say, stop trying to build a path like we usually do from a higher rank graph, and instead consider the dynamics of the category lambda itself. So he studies partial bijections of lambda that give rise to these constructible right ideals, is the name that they go by when you're looking at the semigroup literature that Shin Lee has worked on quite heavily. And what these constructible right ideals look like, they are the domains of the possible partial bijections of lambda I could look at. And if we look at the vertex V here, and I look at all possible constructible right ideals based at V, then I get this this partially ordered set of domains of sensible partial bijections. one, no, two, um, and what Spielberg shows is that if you, instead of trying to make paths subsets of the graph itself, if you try to look at filters of these uh, partially ordered sets of ideals in the category itself, then you get a better notion of path for the non-finitely aligned setting. And the connection is this, that if you take a filter like this one here that I've circled, um, in the finitely aligned setting, there'd be only finitely many things below this bottom element, and Spielberg's theory would say that that's not allowed. You have to go down further. But when you have one of these things that can't be covered by the finitely many things below it here, that means that when you try to produce some kind of a nice subset of your category from it, you end up with just this corner of the graph because the only principal things in this filter are, are v, lambda, and mu. So in some sense, the paths that Spielberg's identifying by looking at these partially ordered sets of constructible right ideals, they don't look like paths at all because it's like just this corner of the graph which is going off in different directions. It doesn't end up anywhere. So the whole idea of a path is lost. Now, just to finish up, what has been interesting recently is that even though these things aren't filters, it's not directed because lambda and mu has no common upper bound. It does turn out to be, in this one example, a thing called a Frank ideal, which is um, it's sort of, I mean, it's something that I'm trying to learn more about at the moment. But the point is that there's other options than filters to consider in some partially ordered set when you're trying to um, do completions of the partially ordered sets, or it kind of depends on the context. But what seems to be happening is that there's a possible way to reduce a somewhat complicated notion of a path to something that's just a subset of the graph itself again. And my hope is that that's going to one day make a really combinatorial approach to the non-finitely aligned setting happen again. Because at the moment, it's very hard to grapple with the non-finitely aligned case. But I won't take any more of your time, and I'm going to call it there today. So thank you for listening.
Uh,
You said that you get bigger and fatter system as their size. I'm wondering, so I know, for example, if you have a single graph system that's got a real rank zero and things like this, and you get something that's not real rank zero, for example, out of these guys, or anything like that.
So I'm not exactly sure about that. But I'm trying to remember that Kumjin and Pask's motivation to develop K-graph C-star algebras in the first place was some work by Robertson and Steger, like the year before. But I'm not familiar enough with that paper either. So I think to see what the motivating class of C-star algebras they were trying to capture is, I would look at that paper by Robertson and Steger. I think.
Groupoids you get always ample still.
Yeah, they are always still ample groupoids, the ones that we're constructing. Even in Spielberg's construction, it's an ample groupoid. Maybe that answers the question. Yeah, okay.
Engage action. They're just a actual key, they'll have key data.
Yes, yeah, that was what I was trying to recall is that somehow this gives you continuous functions on a k-dimensional circle instead. Yeah. No idea. That's the thing is that yeah. I bet that Jack and his group have talked about that though, because they do a lot of work in gauge invariant uniqueness theorems. In fact, maybe they do have a paper. Jack Kolozewski and a couple of others, which perhaps had motivated him to start developing his very, very general framework with just left cancelled of small categories. Uh, so perhaps I'll look up a reference for that and send it to you.
Yep. 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 So maybe I missed it, but so is the path groupoid where you take a k-graph? Is this a groupoid?
Yes, yeah. It's the path group. What if you take a k-graph instead? So we have multiple ways now of doing path spaces and defining shift maps. But if you take this map here on filters, and then uh, you change nothing here because I wrote it down so loosely. But you just imagine that the x's and the y's are coming from the path space in k dimensions. Then it is a groupoid.
So it's a proper groupoid. It's because you might think that maybe you get something like a k groupoid, like a higher
like the
category.
groupoid itself gets higher dimension. I see what you're saying. Yeah, no, the groupoid itself is still just a groupoid.
And you don't think that there's some k groupoid lurking in the background?
Yeah, well, there are. This is sort of more on the category theory side, isn't it? That there are sort of in categories that people study. But I'm if that's the kind of thing that you're thinking of, but I hadn't even thought about it, so I should look that up.
Yeah, like I was just thinking that it might be something like this when you drew this picture here for k equal 2, because I don't know if this is the right way of thinking, but I don't know, you might either think of this extra dimension as going up or going down, or maybe of moving the morphisms so that it's so in a 2 category, you would have also morphisms of morphisms.
Yeah.
So it's.
Oh, that's interesting. Yeah, okay, I'll look into that.
And then things like, I don't know, being an open invariant set might be that you do not only need to check if the paths are kind of ending up in the subset, but maybe also like if you have arrows that are now mapping paths into other paths, they should also stay inside of this subset. But okay, that's very vague. I don't know if this makes any sense.
It sounds like an interesting thing to look into because I know that it can be quite fiddly handling these many dimensions just in a one groupoid, if you like, because even trying to define a sink in a directed graph, you would just say, well, it's something that there's no paths going out of that vertex, but in many dimensions, you have to check one at a time and say a sink would be something so that there is a dimension I can escape in. So all of the definitions for sinks or cycles and graphs get much more complicated in k dimensions. If there was some framework that did all of that automatically, it would be really nice. I'll look into it.
Well, actually, yeah, I just have a quick question. So, yeah, so you define the K graphs as well as actual categories, right? Like, so, but there was some the original notion of a K graph was you have some kind of graph and you have some coloring or some kind of some more complicated function on the edges, right? Like, and then somehow actually build some kind of parts and then get your category, I guess, that way.
Yeah, that's right. So you can say that K graphs are in correspondence with a graph with certain coloring mappings that are doing the solid or dotted line like over there. But then it's a really technical theorem just to say, if I draw a graph and color it, can I check that this actually does arise as a K graph? It's very complicated to do that. So I think that's one of Jack Spielberg's complaints is that it's not even that combinatorial to work with K graphs in the first place because I can't just draw a picture and think that it's going to be a K graph. So he sort of moves into this even more general framework where you've got a bit more flexibility that makes it easier.
Yeah, no, I definitely find this a lot easier to follow than the original stuff I saw on K graphs. So yeah.
If you just think it's a category and there's some functor, the degree map, which is controlling it. Yeah.
Cool.
Okay, there's no other questions, then let's thank the speaker again. Yeah, why not? And next week, Aaron, or
Okay.